the honest old-fashioned way. And but I'd like, if it's possible, I mean, this is a very interesting discussion, but it's going to go completely off. So I'd like to stay on track and maybe have that discussion at the end of the talk. Okay. I mean, I think it's a very interesting question, but it's sort of orthogonal. And in my view, it's a constraint, it's a consistency condition on the string theory landscape. You want that to be stable enough but not too stable. Okay, so the main model that I want to get out of here is that we don't want to make the mistake of rewarding a vacuum for sitting around doing nothing for an exponentially long amount of time. Okay, and these factors are huge. So as a zero order approximation, I want to do better than that. And what we're seeing, of course, in our own vacuum is that, you know, even if it lives for an insanely longer time, subtlety, everything interesting happens at the beginning. Okay, everything interesting happens when the bubble is created between that time and the time when everything's thermalized and the de Sitter space is emptying out. It's the out of equilibrium period that's the most interesting period. Okay, that's when complex structures can form. That's when the global observers arise. And I'll get back to that point when it comes to the question of weighting vacuum in more detail. As a zero order approximation, what I want to take away from this is that the most important thing is to just get into your vacuum. It's just producing it. You know, of course, you don't want it to decay very, very fast. But compared to the exponentially long time scale we're usually talking about, the good first approximation is just being interested in the expected number of times the world might going to enter a given vacuum. That's when there's potential for something interesting happening. Okay, so that's what I'm going to compute. And in order to compute that, it turns out that you don't need all of the information that's contained in this matrix kappa. Because you don't really care how long this vacuum lives. When you're in A, you're only interested in where am I going to go next, not when am I going to do this. So what's the relative probability to decay into B or C or D? And the relative probability I can compute by dividing out by the probability to decay at all, okay, which is the probability goes from A to all the different J's if you go to. And so I get a matrix that is contains less information in the sense that you guarantee that all of the columns here sum to 1 except for the terminal vacuum, which is still 0, and which you don't normalize this way. Okay, so here's a vacuum A that has to go to B. Remember the drawing. B can go back up to A or down to Z, and there's one free parameter here. It has to add to 1. It has to decay at some point. And Z doesn't go anywhere. Okay, so this is important because it means that these exponentially small numbers have, while it's not gone away completely, that the epsilon might still be very small, at least we've gotten rid of some of them. And in fact, if this epsilon is very small, then we can practically replace it with zeros. And we'll have only 1 to 0 in this matrix. So this is important because from this matrix you don't generically expect to get exponentially large numbers anymore. So how do you compute the expected number of times that you enter vacuum, let's say A? Well, one way to do it is to draw a tree, where you start in vacuum A, let's say, and then the only thing that can happen is probably 1 if you go to B. There you have a choice. You can take advantage from this eta matrix, go to Z or to A with these super probabilities. So you draw this infinite tree, and now you look at all the different ways you could have gone into A. Okay, so there's one path with probability epsilon, you multiply these. There's another path with probability epsilon squared, and so on. And so your total expected numbers to get into A is epsilon over 1 minus epsilon. Then you do similar things for B and Z, and in order to get normalized probability stuff, you divide by the sum, and you get these answers. And this just demonstrates it's very straightforward. In fact, it's more straightforward than this because you can show that you would have gotten the same answer that you had stopped at any time that you got back